Yeah, okay, thank you. So this is going to be a very introductory talk. I didn't know what is the level of the audience here. So this talk is very introductory. Please feel free to ask questions, to interfere. I enjoy it when it's interactive. And if you feel that this is too introductory, then I will do more technical topics in the second half tomorrow. So this is just an introduction to the theory of machine learning. And basically, I'm the same spirit of my book. So, okay. So it is not about how amazing machine learning is. You already know it. And I'm not going to show you any videos of fancy applications. And the talk is more on the why machine learning works rather than how to make it work. So yeah, I will focus on understanding the principles that underlie machine learning. So I like to start my talks on both on machine learning and clustering is these citations from Herbert Simon. It says that the purpose of science is to find meaningful simplicity in the midst of disorderly complexity. So this is a very nice definition of what science is, but I feel that it's also a very good definition of what machine learning is trying to do. You get very large and complex data, and we are trying to find some meaningful, simpler patterns in this data. I would define it as really the first goal of machine learning, at least statistical machine learning. Okay, so statistical machine learning, we are trying to find algorithms to detect meaningful regularities in large complex data. And we usually focus on data which is too complex for humans to figure it out. And we try to learn from random samples from this very large data. So we have very large data, we take random samples, we're trying to learn about structures in the data from the random samples. I'm sure that you all know it. So the motivation that I like to start with is the story of bait shyness in rats. So what is bait shyness? If you try to poison rats with baits, then the rats are very smart. If they see a piece of food that is not familiar to them, they will only take a very small taste. And if a few hours later they feel sick, then they will never approach this food again. So if you try to put baits for rats, you're not killing them. They will just take a small taste. They feel sick. Hours later, they connect it to the small piece of the new food, and they will never touch it again. So this is an example of an amazingly successful learning. They learn from one experience, and they avoid this food forever. If you want to know how people really poison rats, what we do is we give them poison with delayed effect. So they eat it, they wait a few hours, they still feel good, so they allow themselves to come back and eat more, and then the next day they feel sick, but it's too late. Okay, so this is a great example of successful learning in nature. So here is the story that I just told you. The rats encounter poisoned food, and they learn the causal relationship between the taste and smell of the food and feeling sick afterwards, and they learn this immediately from one trial. So here is another example of not so successful learning in animals, and this is the famous experiment by Skinner. So Skinner was he was one of the founders of behavioral psychology about 70 years ago, and he was trying to show, behavioral psychology is trying to show that people are not very different than animals, as opposed to personal psychology and Freudian psychology that try to say that we all have very unique experiences. The behavioral psychology is saying we're not very different from animals. And here what he was trying to do is to show how you can induce superstition in pigeons. So what he did is you put the pigeons in a cage, and you put in the cage several toys, and then you don't give them food. And at random intervals, once they get hungry, at random intervals, there is an automatic spray that sprays grains into the cage. So the pigeons get hungry. Eventually, suddenly there is a spray of grains, and they eat, they're happy, and then you wait and wait and wait, and they get hungry again. And then at a random time, there is another spray of grains. So what happens after like 30 such iterations? So when pigeons are hungry, their instinct for searching for food is to peck around. So when the pigeons are getting hungry, they start pecking around, and then suddenly there is a spray of food. So every pigeon begins to connect the spray of food to the toy that it has been pecking at this time. So after each successful feeding, they increase their tendency to be near that toy. And when it repeats over and over again, they get reinforced that this toy is really bringing food. So after 30 iterations, each pigeon is obsessively pecking at a specific toy that they believe that this is what brings food. And they get reinforced. They pick this toy and really food occurs. So he used it to demonstrate how superstition is being created. And superstition is something that, I mean, we all have with humans as well. I mean, you know, I am Jewish and I come from Israel, and in Israel, the seasons are very organized, they're very systematic. The rain only comes in the fall. So at the beginning of the fall, we have special prayers for rain, and we do these prayers at the beginning of the fall, and indeed, the rain comes. So we behave exactly like the pigeons. So we have here two examples of learning. One is successful learning of the rats, one is a very stupid learning of the pigeons. And what I want to try to understand is what distinguishes these two types of learning. Why are one of them doing so smartly and the other one are so stupid? So in what way are the rats smarter than the pigeons? So in 1988, a PhD student in Berkeley, Garcia, he was trying to investigate what makes the rats so successful. So what he did is that he gave them poisonous food that looked exactly and smelled and tasted exactly like the food that they usually get. They just added tasteless and smellless food, poison into the regular food. But of course, in such a case, the rats have no clue how to avoid it. So what he was trying is he was trying to give them a different warning, say a noise or an electric or a flash of light. So every time the rat tried to eat from a poisonous bait, there was a flash of light, and when he tried to eat from a non-poisonous bait, there was no flash of light. So it looks like exactly the same situation. Now, what do you think? Did the rats learn that when they feel sick, it is because they tried to eat something when there was a flash of light? Do you think the rats learned this connection? And indeed, you're guessing right, the rats did not. Surprisingly, they failed to detect the association. And he was trying it with a flash of light, he was trying it with a ring of a bell, he was trying it even with a small electric shock. They didn't connect it to feeling sick afterwards. So one can think, I mean, why is nature so stupid? Why can't we have super rats that will pay attention to noise and will pay attention to light and will pay attention to electric shock, and then they will be able to also avoid the poisonous bait in all those situations? Why are they so limited that they only respond to the taste and the smell? And the answer to this, it's not that nature is stupid, the answer is that these improved rates, will they survive better? But what will happen with these improved rates? With the improved rates, every single time you eat food, there is something special about it. So if I feel sick tonight, and I will think, oh, it's because when I was having my breakfast today, I was sitting in a balcony, and I usually don't sit on a balcony. So I will try to think I'm probably sick because I was sitting on the balcony on breakfast. And it doesn't work like this, because if we are sensitive to every possible clue, then every event is unique and we cannot learn anything. Nothing repeats itself. So that's the main point here, is that what makes the rats so successful, they will not know what should be blamed for the sickness if they were sensitive to all kinds of stimulus. So they are genetically engineered to pay attention to the taste and the smell, and not to noise or light or anything else. So the lesson from this is that the key difference between the rats and the pigeons is that the rats have a prior knowledge. They have prior knowledge about what can cause sickness. It's the smell and the taste, and it's not the noise or the light. And the lesson from this to us when we want to design machine learning is that prior knowledge is essential. You cannot do without prior knowledge. I mean, that's one of the lessons that machine learning people used to be very aware of, but now they start believing that they will have general machine learning and they will not need any prior knowledge. But we can prove that you cannot learn anything without prior knowledge. So I think that there is, before I move on, there is a very natural question to ask here. And this is, but how did the rats learn that what they have to care about is the taste and the smell? I mean, this is in their genes, and they learn that, I don't know, when the rats were created, they first appeared on Earth, did they also have it? So what happened is, through generations of genetically natural selection, they really learned that they have to pay attention to the smell and the taste and not to other stimulus. But this process of learning through generations and generations of natural selection and collecting a lot of data requires more data than we can feed our machines when I try to train some machine learning algorithm. So there is really, they really basically learned from scratch, but it took generations, and a lot of stimulus and experiments. So the conclusion here is that this is the basic no free lunch principle, is that no learning algorithm can be guaranteed to succeed on all learnable tasks. And every learning algorithm has a limited scope of phenomena on which it can succeed. This is the inductive bias. And no learning can be successful, guaranteed to be successful, without prior knowledge. I mean, this is a theorem that we can prove. I will not prove it here, but we can show that if you try to learn without any prior knowledge, the size of data that you need is roughly the size of your domain. So you have to see every possible instance several times. That's the only way that you will be able to learn without prior knowledge. So it's like, if you want to learn without prior knowledge, sure, you want to learn to distinguish cats from images of cats from images of dogs. But if you start without prior knowledge, you will need data which is the size of all possible images, which is completely inconceivable. So that's the basic first principle. We need prior knowledge, and we can prove it, and that's called the no free lunch theorem. You can see, I can talk about it more if people care about proofs, but not right now. So there can be no best learner. Every learner has its inductive bias. It is good on some type of tasks, but it will not be good on other tasks. Okay, so this is the no free lunch theorem. And this is something that I encounter all the time. I mean, people come to me. I'm a professor of machine learning, and they come to university and they want to help from machine learning. So I had this experience with doctors. They say, I'll give you my data, you will crank up your smart machine learning and give me some meaningful insight. I had this experience with doctors. One of the big struggles of modern medicine is with Alzheimer's disease. Doctors don't understand what caused it. And they have tons of data. They do research over years. They follow 10,000 patients year after year after year and trying to see who develops Alzheimer's disease and try to see what it's connected to. So they come and give me all this big data and tell, you know, put your machine and tell me what causes Alzheimer's disease. And if I tell them it doesn't work like this, I cannot. So they say, okay, we can give you more data. And if I say, but it still doesn't work, then they say, okay, so we'll find another advisor. But basically, we really need prior knowledge. If you want to apply any tool of machine learning, you need to communicate with the domain expert, and you need to learn from the domain expert which features are relevant, which type of hypothesis may work, and so on. So that's my first message, is the need for prior knowledge to incorporate in any learning task. So we need domain-specific prior knowledge, and the first challenge, maybe high-level challenge, is how should we model prior knowledge? And there are many, many ways that we are trying to model prior knowledge. So we need tools that on one hand will be understandable from the domain expert, and on the other hand will be useful to the design of a learning algorithm, because we want to communicate with domain expert. And that's the big, I think, one of the big fundamental challenges of machine learning. So the simplest, the most maybe established way in terms of theory, not in terms of how practical it is the notion of a hypothesis class. So you restrict the set of potential predictors. Say, for example, I want to predict with a linear classifier. So I want to know if you are likely to get a heart disease or a heart attack. So I take your features, which is your heartbeat rate, your weight, your age, your blood pressure, and I write a linear classifier. I say that your probability of getting a heart attack is 0.1 times how overweight you are, plus 0.2 how bad you eat, minus 0.3 how well you exercise, and that's a linear classifier, and I have a threshold, and I can tell you, I can predict with this threshold. So that's a kind of hypothesis class. My hypothesis class is all linear classifiers over the set of features that I get from my patient. That's one way of incorporating prior knowledge. But of course, it could be that the likelihood of a heart attack is much better predicted with something which is not linear. And other tools, like kind of tools that we use, is regularization principles like description lengths. You probably heard about this minimal description lengths. The shorter the description lengths, the better predictor it is. So where does the prior knowledge come when I talk about description lengths? I mean, if I say the best predictor is the one which is the shorter description lengths, and I prefer one that has a shorter description than another, and I can even prove results about it. But a minute earlier, I said that there is no general learner. So where is the prior knowledge comes when I just look at the description lengths and want it to be as short as possible? Anybody? What? Yeah, it's kind of, it's in this, the definition of in what language I use to describe things. Because I can switch from one language to another, and something that was very short in one language will be very long in another. I mean, you can see it in programming languages. If you have a high-level programming language, you can give them one command, but if you wanted to write it in a different programming language, it will have very long lengths. Or in human speech, say, I want to say, this is a joke, and everybody will understand. But if I want a machine to read it, then joke will not be just 4-letter word. I will have to give it a very detailed, long description of what a joke is. So the prior knowledge here, when we talk about description lengths, it comes through the choice of language. And things can go completely opposite if you switch from one language to another. Another way of incorporating prior knowledge is margins. You prefer classifiers that have larger margins, or sparsity, We want sparse classifiers that rely on as few as possible features, or low norm. There are all kinds of principles. They all try to inject prior knowledge into your learning method, and we cannot do without prior knowledge. Similarly, there is a notion of kernels. Oh, you will have a talk about kernels by Arthur Breton later, I think next week. But kernels are also a way of incorporating prior knowledge. A kernel is a notion of similarity, and we want this notion of similarity to be relevant to the thing that we are trying to predict. So for example, if I try to predict the response of people on Facebook to some advertisement, then we can define a kernel of a people by saying the similarity between two people, P and Q, is, say, the number of common Facebook friends that they have divided by the total number of Facebook friends that they have. So this is kind of a notion of similarity between two Facebook pages or two Facebook people. It may be very successful if I'm trying to predict whether they will like some news item or not, but it's going to be very bad if I'm trying to predict who is taller than the other. So it's really based on some domain knowledge of what I'm trying to predict with it. So this is another way of incorporating prior knowledge with kernels and of course with neural networks. So what in neural network, where do we inject the prior knowledge into a neural network or a deep neural network? In the architecture of a neural network. We may have time to talk about it later. Of course, the ultimate neural network will be a neural network in which every node is connected to every other node. But if we have so many connections, then we are going to fail in different ways, in overfitting. So we have neural networks that have only very limited number of edges compared to having all possible edges. And the choice is the architecture of the neural network depends, of course, on the prior knowledge on what you're trying to do. So if you're trying to do image classification, you're doing one type of architecture. If you're trying to do gene sequencing, you're using a different architecture. And another type of introducing prior knowledge is when you're doing Bayesian learning. I don't know if you have any talk here about Bayesian learning in this workshop, but in Bayesian learning, we introduce the prior knowledge by saying we have some notion of prior likelihood of which models could reflect the data better. And our success depends on how close is this prior likelihood to reality. Okay, so the first part of it, all I wanted to tell you is that we need prior knowledge, and there are many different ways of introducing prior knowledge into our learning. But every learning tool has some either explicit or implicit way of an inductive bias. It is good for some tasks. It will not be good on other tasks. Okay, so let me move to some formality here. So, okay, so we are going to look at many detection tasks. I don't want to list them here, but so we will talk about some domain set X, and then we have a label set, which is, say, for simplicity, let us just try to predict a binary label, success or failure, heart attack or not heart attack, and so on. Now we will talk about a very concrete task in which you get supervised learning, which you get a training sample, which is a random set of points which are labeled correctly. And then the output is a prediction rule. So I guess you all know it. We get a supervised randomly generated data, set of images. Each image is labeled whether there is a cat there or not. And now you're trying to come up with a rule that takes an image and predicts 0 or 1 according to whether there is a cat in this image or not. Okay, so that's the basic. And we assume that the distribution that generates the instances is unknown to us. And there is some unknown rule, which is really the correct ground truth, whether there is a cat in the image or not. And we define the error of the classifier as the probability that our classifier will make a mistake. So that's kind of the very, very basic starting point for formalizing supervised machine learning. That's clear to everybody, right? Okay, so given a labeled sample, we also can define the empirical error. So if I have some hypothesis H, I define the empirical error of the fraction of points on the sample on which I err. So notice that what we are trying to predict is what is the probability that we'll make a mistake, but what we can measure is the fraction of mistakes on our training sample. So that's called the empirical risk. And the very, very first basic principle is find the minimizer of the empirical risk. So find the hypothesis that on the sample, which is all the information that we have, it looks as errorless as possible. Now, what's wrong with such a principle? I mean, that it seems like the most intuitive thing to do. All we know about the world is a sample. You showed me a set of pictures. You told me here is a cat, here is no cat. And what I will do is I will find a classifier that on the sample makes no errors. The problem is, of course, that this can be very bad. In what sense it can be very bad? Assume that what I will do is the rule that I will learn is that if the next image that you show me is one of the images before that said there is a cat, I will say cat. And if the image that you show me is something that I've never seen before, I will say there is no cat. So now my empirical error, what is my empirical error here? What is my error on the sample? On the sample, it's 0. I'm perfect on the sample, but I'm not going to predict well in the future. So clearly the error of the sample is 0, but of course, there are many cases in which this may be very bad in the future. So here is an example. Say that the ground truth is all blue, and I get this sample. The stars is the sample that I see, and all the points in the sample are blue. So my prediction is going to be blue if you are one of these points, and orange if you are outside. And that's, of course, going to have a very big error when the ground truth is like this. So just doing empirical risk minimization is prone to this phenomena that we call overfitting. You really fit to the data and you don't generalize. So what's the next step to overcome overfitting? So as I mentioned before, we have to introduce prior knowledge, and we can introduce prior knowledge by saying we have a hypothesis. We only consider hypotheses from a given set of hypotheses, and now we're doing empirical risk minimization with respect to the hypothesis class. So say I only want to predict with linear classifiers, so now I'm trying to find a linear classifier that makes as few errors on the training data as possible. So that's a revised empirical risk minimization. We limit it to a given hypothesis class. And the first result that we can easily prove is the first guarantee of success is that if the class that you limit to is finite, then we can guarantee success. What does it mean? That for every epsilon and delta, we have these two parameters. Epsilon tells me how much error I can tolerate, and delta tells me how likely it is that I will have error bigger than this. And we can have any ERM-H algorithm, if S is big enough, can guarantee that we will succeed, that we will not make error more than epsilon if we train, if the sample that you train on is not very, very unfortunate. Only delta fraction of the samples will make me fail. So that's the first result. If the class is finite, we can succeed. ERM with respect to the class is guaranteed to succeed. But of course, this is very limited because in reality, we never consider only finite classes. Even the example I gave you before, if I talk about all linear classifiers, so there are infinitely many linear classifiers, even if I only have dimension 1 of the data. So we have to move beyond that, and say we want to predict with the class of all intervals. So say we just want, I just have the my data is only one-dimensional. I just know the weight of a person. This is all the thing and everything I know about the person is their weight. And now I'm trying to predict whether they're prone to heart attack or not. So so I can say there is an interval on the line that will be the best prediction if I just predict depending on the weight or on the, and then the question is, can we learn it reliably? And the answer is yes, although there are infinitely many intervals, we can reliably find out a good interval. And the crucial parameter here is the visit dimension. So I don't know how many of you are familiar with the visit dimension. Most of you? Okay, so the visit dimension roughly characterizes the ability of a hypothesis class to be successfully learnable. And we have this definition, what does it mean to be pack learnable? You are pack learnable if you have some size bound for a function mh that when I give you my accuracy epsilon and my probability of failure data, this is all you need to know is this epsilon and delta, and you can tell me how many samples will I need to guarantee that the probability, sorry, just go back. The probability here, can you see my cursor? Yeah. The probability here is over the samples. The probability over the samples that my probability of error of A of S, A is my algorithm, S is the sample, so my algorithm learned from this sample. So this probability depends on which sample I gave the algorithm. The probability that whatever the algorithm learned will have error bigger than epsilon is less than delta. So the main thing here is that I don't make any assumptions about how data is generated. It's completely without any, but I can give you a guarantee of successful learning. But this guarantee of successful learning is for a class that has to satisfy two requirements. One requirement is that the class has a finite visit dimension, and the other requirement is that one of the members of the class is really a successful, perfect learner. If we have these two requirements, then we can get such a guarantee. Now, it brings us to questions: which classes have finite visit dimension? And then how can we guarantee that one element of my class will be a perfect classifier? So for example, if I look at linear half spaces, and I try to learn with a linear predictor for the probability of heart attack, it's not likely there's going to be a linear classifier that will be always correct in predicting whether my patient will get a heart attack in the next week or not. So these are the two issues we have to address here. What is the visit dimension of classes that we use in practice? And what do we do with this requirement that one of the elements of the class is a perfect classifier? So this is called the realizability assumption. Let me first address this. The realizability assumption is the assumption that one of the elements in my class is a perfect classifier. And this is obviously a very unrealistic assumption. We never really have this kind of confidence that the small class that we came up with contains a perfect classifier. So how do we relax it? And there's another issue, and that's that non-determinism, because what I don't see, as a learning algorithm, I don't see a patient. What I see is the set of features of the patients. So I see their weight, their blood pressure, their heart rate, and so on. But there could be two patients with the same vector of features, and one of them will get a heart attack and the other will not. And the only way we can model this, because we cannot see everything, we cannot measure everything, the only way we can model this is by assuming that the labeling is not deterministic, but probabilistic. So I can ask you, if these are your features, what is the probability that you will get a heart attack in the next week? Because it is not fully determined by the feature that I can see. So once that it's not fully determined by the features that I can see, of course, I cannot assume that I have a perfect predictor, because my features do not allow me this. So we want to address this as well in our theory. And we have a kind of a more general formalism, and the more general formalism that allows this is that we have a general notion of a loss. And the loss takes a model that you come up with, say some linear classifier, and it takes a point, which is a patient and whether it got a heart attack or not, and gives you a number, which is the cost. So it's a more general setup in which I have an abstract notion of a loss. I have a model, I have an instance, and now I have a definition of what is my loss over this instance. And in this general notion, I can define the success of a classifier as the expected loss of this classifier. So I have a classifier H, and I draw randomly a point Z for my distribution, and then I look at the expectation of the loss of my classifier on this point. And this can incorporate much more general situations. So it of course captures the 0-1 loss. I can define my loss as saying 0 if I predicted the label correctly, and 1 loss if I predicted 0 when it was 1 or the other way around. It can capture regression loss. So if you're trying to predict some real valued number, you can say if I have a predictor, which is a function, and I have a point, then my loss is the square difference between the label of the point and my prediction. Say I want to predict the temperature tomorrow at noon, so my loss is going to be the difference between what my predictor did and the real temperature tomorrow, and I square it just for mathematical convenience. Another way of showing how general this notion of loss is in k-means clustering. So I don't know how familiar you are with k-means clustering, but basically you can think about it. You want to find the location of, say, you want to open a franchise of pizza, and you are coming to your city and you want to define, you have the budget for 5 locations of pizza shops, and you want to know where to put them. And now you can define the loss. If I decided that I put the shops in certain vector of locations, 5 locations, and now there is a customer, and the customer wants to buy pizza. What is my loss? My loss is the distance of this customer from the closest store that I opened. So now I have here a model of, I have a model H, which is these 5 locations of my stores, and I have an instance, which is a customer, and the loss of this model on the customer is the distance of this customer to the shop that is closest to it. And I can now try to do machine learning in order to learn what is the best model, where is the best points to locate my 5 stores. So this notion of general loss applies to many more situations than just predicting yes or no. And maybe I'll talk tomorrow more about clustering, but that's a very good example that we can apply the same theoretical framework, the same kind of results to these general losses. And another kind of a loss is what we call a confusion matrix. Maybe you're trying to predict, you have an image, and you're trying to predict, is it a cat or a dog or a horse? So I can write here a matrix of, on one hand, I have my prediction, on the other, I have the truth, and I can say, if I predicted a dog and it's a cat, then my loss is 0.2. But I predicted a dog and it was a car, then it's a really bad prediction. And such a confusion matrix can also capture, you see, this confusion matrix here is symmetric. If I predicted a cat and it was a dog, I'm paying the same loss as I predicted a dog, it was a cat. But in reality, there are many situations in which prediction is not symmetrical. So for example, if I have a self-driving car and I predict that it's a pedestrian and I stop and it was not a pedestrian, the loss is much less than if there was a pedestrian and I predicted, no, it's not a pedestrian, keep going. Then my loss will be much bigger. But I can also, of course, reflect it in such a matrix, but the matrix will not be symmetrical. If I predicted pedestrian and it was not, then it's a small loss. If I predicted not, and it was a pedestrian, it's a big loss. So what I'm saying is that this notion of loss can be general, very general. It can capture a lot of phenomena, and it can capture also this kind of confusion metrics. And now we can get general results for learning with those general losses. So we have this notion, a definition of what is successful learning. So here we have a definition of agnostic path learnable. And the agnostic comes to say is that I got rid of the assumption that in my class there was a classifier that did perfectly well. So what is the definition of success here? So reading it through is not so important, but the main thing is the bottom line. The bottom line is that what I guarantee before, what I was trying to guarantee is that the probability that I will make loss greater than epsilon is, I have here, this should be greater than. Because I want to say that the probability that the loss, the expected loss of what I learned, so I had a sample S, and I applied my algorithm A, and I learned a model A of S, and now I look at the probability that this model will incur loss. What is the expected loss of my model on the data? And the probability is, this should be the other way around. It should be less than. The probability that the loss will be less than this expression plus epsilon is less than delta. So if you compare it to what we had before I didn't have this part. What is this part? This part tells me I compare my loss to the best in the class. And what I can guarantee to you is that I will not be much worse than the best in the class. So before we had exactly the same equation, but I didn't have the blue part here. If I assume that I have perfect classifier in my class, I can try to guarantee that your loss will not be more than epsilon. If I don't have the perfect classifier in a class, all I can guarantee that I will not be more than epsilon than the best in the class. So there is kind of two different setups. The realizable setup is that we make a very strong assumption. We assume that we have a classifier that will make zero error, and in return, we can get an absolute guarantee. We can guarantee that your error will not be more than epsilon. On the agnostic case, we make no assumptions, but the guarantee is only relative. So I don't give you a guarantee that you will not make error more than epsilon. I give you a relative guarantee compared to the best in the class. So an example that I like to make is say that you have two banks that are trying to convince you to invest with them. And one bank tells you, I guarantee to you that you will make 5% every year, provided that there is no war and there is no tsunami and there is no big earthquake anywhere on Earth. So he makes assumptions, and under these assumptions, he gives you a good guarantee, you will get 5%. The other bank tells you, I don't make any assumptions. Under any possible situation, what I guarantee to you is that you will do as well as the best bank in the city. So maybe there was a catastrophe and all the banks in the city really did badly. I cannot guarantee anything. But that's the relative guarantee. One of them makes assumptions that give you a concrete guarantee, but if the assumptions were not met, you are lost. And the other one makes no assumptions, but only gives you a relative guarantee relative to some benchmark. So here, my class of models H is my benchmark. My guarantee is that you will not do much worse than the best in my class of models, or than the performance of the best investment agency in town. Okay, so these are two different setups, the realizable setup versus the agnostic setup. And agnostic says we don't make any assumptions, but the cost is the guarantee is only relative. Okay, so can we do anything? Can we get those agnostic guarantees? And again, the crucial factor is the visit dimension of the class. If my class of models has the fundamental theorem of statistical machine learning, says that a class of models is agnostically Pak learnable if and only if it has a finite VC dimension. So VC dimension is defined for classifiers which are binary, just predicting 0 or 1. If we want to predict a set of labels, dog, cat, horse, cow, and so on, then we need to have a variant of the VC dimension. But in general, we have those combinatorial dimension, and you can guarantee success of learning if and only if the dimension of the class, the relevant dimension of the class, is finite. And one algorithm that seems to always work is the minimizing the empirical loss. So here, you see, I'm repeating what I did before, but now I'm doing it in the agnostic, in the general model. So here, the loss on a sample, I have a model H, and I have a sample S, so the loss of the sample is just the average loss of H over the points on the sample. And empirical risk minimization is trying to find a member of my class H that minimizes the loss over the sample. So before, the loss over the sample was counting how many times I mispredicted, but here I just take the average losses over all points because we said loss is a very general notion. And it turns out that this algorithm will succeed whenever it is possible to do well. So it turns out that this very simple classifier that says you have a class of models, you want to guarantee that you will behave as well as the best in the class. All you need to do is find, given a sample, training sample, find a model in the class that minimizes the loss on the sample. If a class is learnable, if it's possible to learn at all, then this simple algorithm, this simple principle, it's not an algorithm, but this simple paradigm is guaranteed to work, and it's guaranteed to have the best sample size possible. So let me, two things now. First of all, how exactly, it not only tells you whether you can learn or not, but it also tells you how many samples you're going to need. And it turns out that the number of samples that you're going to need in the worst case is this VC dimension plus log 1 over delta. Remember, delta was the probability that I will get a bad sample that will not help me, and divided by epsilon square. So this is kind of a general bound. No matter what the data is, I guarantee to you that if you have this size of training sample, you will do epsilon delta well. Or in other words, that if you have this sample size, then your loss of your algorithm, even if you just do ERM, will be at most the loss of the best in the class plus this quantity, which is the VC dimension over the size of your sample. So the larger the sample, you see here, you need a sample that will be at least as large as the VC dimension. Because your loss, this is the probability of failure. The probability of failure, once you pass 1, I give you no guarantee. So I need this term here to be small. So I need the sample size to be much bigger than the VC dimension of the class. So it follows that we need training samples that are at least the VC dimension of the class. But if we have it, we have this kind of guarantee on our added loss compared to the best in the class. So I think the next obvious question is to ask, so what is this mysterious VC dimension? What is the VC dimension of classes that we really care about? So let me just look a little bit at this. So, and first of all, it's a worst case guarantee. It tells you that no matter what the data is, if you have so many samples, if the number of samples is proportional, is bigger than the VC dimension, you'll get this success guarantee no matter how data was generated. So this is a worst case guarantee. It is a guarantee, it always holds, but it is very pessimistic. In reality, things can be much better. You can error will be much less than this, but this is the worst case of the error. Okay, so what is this visit dimension? So roughly, I will not go to definition, the technical definition, maybe many of you know it, but the main thing to note is that as a rule of thumb, the visit dimension of a class is the number of parameters you need to zoom in, to fix, in order to zoom in on a specific model in the class. So for example, if I have linear half spaces in RD, in order to define a linear half space, I need D plus 1 many parameters. I need D plus 1 coefficients. I need A1x1 plus A2x2 plus ADXD, maybe plus a threshold B. So the number of parameters that you need in order to specify one half space among all the half spaces in RD, you need to fix D plus 1 parameters, and that's the visit dimension. That's the crucial factor. It means that if you want to learn half spaces, you will need sample size, which is in the order of the dimension of your space. What will it guarantee? That you will do as well as, close to as well as the best linear classifier. For binary decision trees, it is the depth of the tree, right? Because if I have a decision tree and I want to pick one branch, which is much model, the question is how much information do I need to give you to determine one branch? So at every node going down, I have to tell you whether you should turn left or right. So the number of inputs that I need to give you to determine one branch is D. So this is the depth of the tree. So this dimension of this is the depth of the tree. What has happened with neural network? If you have a neural network, you have a big neural network, and you want to fix one function, how many parameters do you need to set? So in a neural network, the neural network is determined by the weights on every edge. So the visit dimension is roughly the number of edges in the neural network. And this is already shows you, you're going to have a talk about theory of neural network. Where is, yeah. So the problem is that in today's deep neural networks, the number of edges is so big that you are not likely to see as many samples. You see that the visit dimension is the number of edges in the number of tunable weights in the neural network. The visit dimension, as we saw before, the guarantee that I can give you is that your error will be less than the best neural network in this architecture, plus this term. And this term is the visit dimension, which is the number of edges divided by the sample size. So if you don't have a sample size which is much more than the number of edges in the neural network, I cannot guarantee success. And that's where this gap between our guarantees are worst case pessimistic guarantees. In reality, neural network work with sample sizes which are less than the number of tunable edges in the neural network. And the reason that they work, we don't fully understand it, it doesn't meet the guarantee. The guarantee is on worst case of all data distributions, and it just turns out that in reality, we are often better than worst case. So in general, the crucial point here is the visit dimension, and the visit dimension is the number of parameters that you need in order to select a fixed function from your set of functions or a set of models. Okay, so far we can think of two parameters that we have to care about when we pick a machine learning tool. One is the expressiveness, and the other one is the statistical validity. So what do I mean by the expressiveness and the statistical validity? You can see it if we go back here to this bound. You see the error that you will get is bounded by the best in the class. So that's a question of how expressive is your class, or how suitable is your class of models to the problem you are trying to model. You will never be able to do better than the best in the class. So the first term grows as the class is more and more expressive, it can express better and better models. The second term is the statistical validity. If your class grows, the visit dimension will grow, and the guarantee here can deteriorate. So we see that when we want to choose a model, we need to take into account these two considerations: how expressive is my set of models, how well it can capture the problem I'm trying to solve, and on the other hand, what is the statistical validity of using such a network or such a model. So here is it in a picture. You can see that what I was trying to say here is say that this is the best function, and this is the class that you pick, the class of models. We did not make an assumption that the class of models contains the best possible classifier. And so this may be the best one in the class, the closest to the optimal classifier, but you have to be inside your class. But of course, we cannot find the best in the class. We can also we only guarantee that we are going to be, if we do epsilon away from the best in the class. So we are going to predict with this point where the best is this point. And we have here a trade-off between this is called the estimation error, the green one, and this is the approximation error. If I make my class bigger, the expressive power is better, the approximation error goes down, but then my statistical validity deteriorates. So we can, many ways of trying to depict this kind of trade-off between expressiveness and statistical validity. So say I have this set of points and I want to find a model for them. So this could be one model and another model could be like this, and the second model is more expressive and it can hit all the points right on the head. And there could be also a very simple model and we have a trade-off between simplicity and the statistical validity, because if I'm trying to predict a new point, I can get better guarantees for simple models, they have low VC dimension, than for complex models. But the complex models are more expressive and they can do better on the training data. So I have several slides that try to depict the same thing. Say I'm trying to depict the label of this point. My training data is these points, so I can do a very coarse grid and takes the majority in every square, and then I will predict that this point should be blue, but I can do a fine grid and predict the majority in every square, and now in this fine grid I will predict that this point is red. And the reason the fine grid gives me more expressive power, but it has less statistical validity. In order to have any guarantees for the final grid, I will need more points. I will need more sample size. Because here, in order to determine a specific function, a specific function here is what is the color of each square. So here, my VC dimension roughly is the number of squares. So if I have more squares, I can express more delicate, more complicated functions, but my VC dimension goes up. In order to get any guarantees, I will need a bigger sample size. That's the basic, sometimes we call it the bias variance trade-off, or the simplicity versus validity trade-off. Okay, there are lots of ways to depict it. You see here, I look at the complexity of my model and I look at the accuracy. And if I have a limited number of samples, if I take models that are too complex, then my behavior, my accuracy will deteriorate due to the risk of overfitting. If I have too expressive model compared to the size of training data, then I may just fit to the data and it will not generalize. Okay. So expanding H gives me lower approximation error, but it increased the estimation error. And the question is, are we done? So now we have these two notions, the expressive power and the statistical validity. We know that ERM gives you best results. It looks like we solved machine learning. We know everything that needs to be done. We know what's the best algorithm. But there is another considerations. We only discussed so far the information complexity. So far, we only talked about how many training samples do you need. But of course, in reality, there is another crucial factor, which is the runtime of the learner. So once you have enough samples, you need to pick the model that is minimizing the error over the samples. And this task can be very, very time demanding. So we need to introduce a third consideration, which is the computational complexity of your class. How difficult it is to find, given a data, how difficult it is to find a good model in your class. And that's a very crucial component. So now we have three components: the expressiveness, the statistical validity, and the computational complexity of finding a good predictor in your class. And it turns out that this is often the bottleneck to machine learning. So, okay, so how much computing you need in order to run ERMH? And we show that for all of those cases, so here is a list of common types of models that people use, monomials, monotone monomials. I will not talk about the half spaces I mentioned. Say you want to predict with balls, say with nearest neighbor, or axis aligned rectangle, or neural networks, or k-means clustering. For all of those, if you fix your class and now you get training data and you want to find the best in the class, the task is NP-hard. NP-hard, I mean, I guess that I will not get into it, but it means that we cannot give you a guarantee that you will succeed to do it. So we cannot give you a guarantee in all of those very practical models. I cannot give you a guarantee that in a limited runtime, you will be able to find this best in class that we showed you guaranteed for in terms of the error. Now, a very natural question should be, I mean, I don't need to find the best in the class. As you, I don't know if you remember, I mean, what we compared is our error, and real error to our error on the data. Maybe it's good enough to approximate the bet in the class. But this is not helping us either. We show that for all of these cases, even approximating, even find a model that is approximately as good as the best in the class is NP-hard. So in terms of worst case guarantees, it seems that we have two big obstacles. One is the sample size. If you have a very complex model, like a deep neural network, you need sample size, which will be bigger than the number of edges by some considerable factor. But another crucial factor is the computational. Even finding the edge weights for a very simple neural network, even for a neural network of depth 2 that has 3 hidden units, it's already NP-hard to approximate the best weights given a training data. You're given a training data, you're trying to find the best weights for the neural networks. It's NP-hard. So what do we do in practice? So what we see now is that we know the neural networks are extremely successful, but in theory, I cannot give you any guarantees because on one hand, the sample sizes are often not enough for the guarantee on sample size. And on the other hand, you need to compute good weights for your network, and finding even approximately best weights is too much computationally. So what do we do in practice? First of all, there are some classes which are easy, Boolean conjunctions. I will not get into Boolean, but decision stamps is an easy class. What is a decision stamp? Decision stamp is that what you do is you project your data to one coordinate and find the best threshold between, say you have a data which is points in RD in high dimension that are labeled plus or minus. They're labeled, this patient is at risk, not at risk, and I measured 30 parameters of patients. So what are decision stamps? I project all the data, I look into only one parameter, only blood pressure. And I found what is the best threshold in terms of blood pressure between patients at risk and patients not at risk. Then I project to another coordinate. Say I project to obesity, and I find what is the best threshold on obesity to predict at-risk patients or not at-risk patients. So in each coordinate, I just find the threshold, and now I say if you meet all those thresholds, then you are not at risk. If you fail any of them, then you are at risk. That's decision stumps. That's a class that's easy to learn. Why do I give you this class that is easy to learn? Because one of the tools that we use, this is a very crude task. It will not do good prediction, but it will do something. And we have a tool that can take classes that do something, which we call weak learners, and crank them into getting a strong learner. So this is one of the common tools to overcome the computational complexities. This is the tool of boosting. So boosting is an algorithm by which you train a weak classifier that is easy to find. It doesn't give you good prediction. All you need is to give you prediction that is slightly better than tossing a coin, than random prediction. And then you take this predictor, you take all the points on which you made errors, you increase the weights of this point, you train another predictor, and repeat it. I don't get into boosting now, but it's a procedure that can boost weak learners that are easy to learn by repeated iterations to get a combination of weak learners that will give you strong guarantees. So that's one way of overcoming the combination complexity. Another way is using a surrogate loss. I'm sure that if you've seen, some of you seen of it, the 0-1 loss is very difficult to approximate, but we have like hinge loss or all kind of losses that come to approximate it. The advantage is that they can be computed more efficiently. They are convex losses. And another is to use algorithms that have no guarantees, and that's what we usually do in practice. So for deep neural networks, we use stochastic gradient descent algorithms. They have no guarantees, but that's what works in practice. And that's one of the many big riddles around the success of big neural networks. I mean, in theory, the size of data that you have, training data may not suffice. In theory, you cannot optimize it. You're running an algorithm that has no guarantees that it does something good, and yet you become a billionaire and famous and everything is working nicely. And the best analogy that I heard on this was that saying that this is like the era of alchemistry, when they were trying to produce, by chemistry, to produce gold. They didn't understand chemistry. They were just doing experiments, but they found many useful chemicals. They didn't manage to get gold, and I think it's the same thing. We will never be able to get general artificial intelligence, but we are very good engineers, and we're finding all kinds of useful things along the way without understanding what we are doing, really without understanding what we are doing. Okay, so that's as much as I wanted to cover in this part. I will be happy to hear your questions, and also about what I'm going to cover tomorrow. I can talk about different things. I wanted to talk about clustering, because clustering is one of the crucial tasks in machine learning. I can talk about learning distributions. You have an unknown data distribution and you're trying to find what this distribution is. And I can also talk about things that connect to what Han will talk later, like fairness. So yeah, I can pick and choose for tomorrow. It will be more technical and more focused rather than general introduction. So yeah.
Okay, thank you very much.
Hi, good morning, and thanks for coming this morning to the talk. I actually want to talk about, I mean, there are lots of stories that I can tell about machine learning, different aspects, and I plan to try to squeeze in 3 topics today. It's actually 3 talks, and I'll see how much of it I can get, and I will try to be as intuitive as possible. I understand that it's a mixed audience. So the first talk that I want to give is about theory of clustering. And this is, I guess that even people who work in practical machine learning, they somehow have to face this issue of clustering. And Yeah, so we have clustering is one of the most widely used tools for exploratory data analysis. We do clustering in social sciences. We cluster groups of friends. We cluster in biology. We cluster genes. We cluster animals. We cluster in astronomy. We cluster in computer science. For example, you cluster faults of a running system to try to understand what is happening. In general, we apply clustering all over. It's a very simple first tool if you have big data and you want to try to make sense of out of your big data. The problem is that we have distressingly less understanding of clustering. So although there are like tens or maybe hundreds of clustering papers being published every year, I claim that we don't really understand what clustering is. And I will try to explain to you in what sense I mean that we don't really understand it. So what I have here is picked from the syllabus of the machine learning standard course second year in Stanford. And here is the syllabus, and you can see that when they talk about learning theory, they talk about principles like bias variance trade-off. They talk about basic statistical tools like union bound or Chernoff bounds. They talk about, and at the end, they give you some practical advice about learning, but there are real principles. That's when they talk about machine learning prediction, classification. When they come to talk about unsupervised learning, which is clustering, I mean, this is just copied from the syllabus of the course. What do we have here? Clustering K-means, EM, mixture of Gaussians, factor analysis, PCA. No principle. These are just a list of tools. It's a shopping list of different tools of clustering, but there is no principle. And it stands in very sharp contrast. It's not a practical course. It's their basic machine learning tool course. And the reason is that we don't really have a good theory of clustering. We cannot say these are principles, these are mathematical underlying tools and so on. And the Stanford example is kind of, you know, that's a great university, very smart people. That's what they can offer for clustering, just a shopping list, laundry list of tools. So what the question should we address? So the first question we should address, if we had a theory, is what do we mean by clustering? I mean, we have an intuitive understanding, but can we give a mathematical definition of what it is? Another question that we should ask is, what is a good clustering? If I give you two different clusterings, how do you tell if one of them is better than the other? What is the notion? How do you measure your success of your clustering tool? Another question is looking at the data. Can we distinguish clusterable data from non-clusterable data? Maybe my data is just smeared all around with no internal structure. Can I define what is clusterable data versus non-clusterable data? Now, to all these questions, we have very intuitive answers, but the intuitive answers are based on data that looks like simple clouds in 2 dimensions, and then you know what you want to do. But if your data lives in dimension 30 or 40 or 200, and you cannot visualize it, and you really need a definition of what you're looking for. And can we distinguish meaningful clustering from random structure? And so these are very good questions, and we don't have, I will try to tell you what kind of answers can we supply and in what directions. I think, I mean, if people are searching for topics to work on, clustering is a very important topic. It's really, really being done all the time. And we are in this situation where you have, you know, like, I used to have a mathematics professor that was telling me that there are different types of birds. When there is a dead animal that's run over by a car at night, there are those animals that will come and eat the meat, but there's also the crows that are very tough, and they can still find food when there are only bones left. So in terms of clustering, there's a lot of meat, It is not, it's a good opportunity to get progress. So, okay, well, let me just demonstrate to you what I mean by clustering is not well defined. So assume that you get this set of, this is your data, and I display it in 2 dimensions. What is the correct clustering of this data? So one option will be, I will cluster it like this, right? Makes sense. There is a small cluster there, there's the big cluster on the other side. Another option is that I'll cluster it like this. This also makes sense. Which of them is better? Which of them is correct? Do we have a notion of correct clustering? And that's on a very simple 2-dimensional example. So the problem is that although it's been applied to many areas, a user needs to choose a clustering algorithm. There are many clustering algorithms available. And not only you need to choose a clustering algorithm, you also need to choose parameters. For example, you have to decide how many clusters do you want. Do you want to cluster it into 2 groups, or do you want to cluster it into 10 groups? So how does the user make those decisions? And the problem is that unlike other computational problems, in clustering it makes a difference. If you want to do sorting, and you imply, and you do quick sort, or you rather do some heap sort or whatever, you will get the same sorting at the end. Maybe one of them will run a little bit faster than the other. But in clustering, if you run 2 different algorithms, you can get results which are completely different. So it is very important which tool you choose. It's not like in other tasks that you can, no matter what you choose, maybe it's run faster or slower. Or in classification prediction, you can always have a validation set and see how well you did on the validation set. But in clustering, we don't have a notion of ground truth. Given algorithms will give us different answers. What should we do? So here is another good example. You see this cloud of data on the left. And if I use, it's clearly 2 clusters, but if I use 2 means clustering, which is a very popular k-means clustering with k equals 2, I will get the picture in the center. And if I will use single linkage clustering, I will get this picture. So you see that 2 different popular clustering algorithms will give me results that are completely incompatible with one another. It's not just, sorting that maybe one element is in one place. So what I'm saying is that it's crucial to be aware of the consequences of choosing a tool. What's the good tool for your data? What's the good tool for your goal, what you're using the clustering for? So let's try to go to basic definition. So how do we define clustering? So if you look at any textbook or whatever definition of clustering, you say, oh, what is clustering? Partition the data into sets such that similar points reside in the same cluster, and these similar points are separated into different clusters. That will be the classical definition. Check clustering online, that's what you will get. That's what we want. But even that simple definition is problematic because often we cannot satisfy both of those requirements at the same time. So let me give you the simplest possible example. Look at this data, very simple data. You just have points which are sitting on a line. And now we want to make it a partition such that similar points are together and these similar points are apart. So I have to tell you what is similar. So pick some alpha and say, if 2 points are closer than alpha, I'll call them similar and I want them to be together. And pick some beta and say, if 2 points are more than beta apart, I will call them separated and I want it to be in different clusters. Now I want to partition this data such that points which are closer than alpha will be together and points which are further than beta will be separated into different clusters. But of course, I cannot do it because if I want every 2 points of distance alpha to be together, I will end up gluing everything into one cluster. But then I will have 2 points which are more the beta apart and they're in the same cluster, and I wanted to separate different points. So you see, even in this most simple example, the definition of clustering, or definition in quotation marks, cannot be met. The two requirements contradict each other. So we have to be more careful about what do we want from clustering to satisfy. So one way to imagine, to visualize visualize the task is to say, we can think of clustering as we have kind of a simplex with different requirements. Say one requirement is that I want to join similar points. Another requirement is I want to separate dissimilar points. Another requirement could be that I want the clusters to be of roughly the same size. Another requirement, maybe I want to be the clustering robust to outliers. But each two of those requirements may contradict each other. So when you want to choose a clustering algorithm, you have this collection of requirements, and you need to choose a point there. To what extent it's important for your task, for your purpose, to satisfy each of those requirements. And indeed, different clustering algorithms, they prioritize different requirements. So for example, single linkage clustering. So I don't know how familiar you are with those very simple clustering algorithms. Single linkage algorithm is an algorithm that just takes the two closest points and say, let's put them in the same cluster. And then you keep going. So at some point you have a collection of the current clusters. You define the distance between two clusters as the distance between the closest points in the two clusters, and you merge the next two clusters. That's single linkage. So you keep merging clusters which are close together, and you need some stopping rule. So single linkage emphasizes that similar points should be in the same cluster. You just make sure whenever 2 points are close, you glue them together. On the other hand, you can think of max linkage. So max linkage is a less popular tool, but what it does is I start by gluing the first points together, but then at some intermediate stage when I have clusters, when I want to decide which two clusters to merge now into one, I'm looking at the maximum distance between points in the two clusters, and I don't want to merge if this distance is large. So you see the single linkage, if I have two clusters, they look at these 2 points which are closest and say, oh, let's merge if these three are close. The max linkage, look at the two most far points from each other and say, if they are far, I will not cluster. So it's a different criteria of how to move. So max linkage emphasizes that these similar points should not fall in the same cluster. It's another very popular algorithm, but it emphasizes the other requirement. Another one is both of them are completely oblivious to the size of the clusters. Because if you do single linkage, you keep merging points which are close, you may end up with one cluster that contains 95% of the points, and then 10 clusters that are very small. But sometimes we want the clusters to be of somewhat balanced size. And none of those algorithms gives any consideration to sizes of the cluster. So for example, k-means. K-means you pick k centers and you cluster points by their closest center, and that turns out to take care of sizes of clusters. It kind of tends to have more balanced clusters. And there are more and more algorithms. And what I want to show you now is that it's not just a matter of different algorithms that will prioritize different requirements. It is also that different tasks ask you to prioritize different requirements. I mean, depending on your task. So for example, consider this is a very important task, deduplication of records in a database. So what is this? If I have a database, say, of patients, and I collected it from many hospitals, it could be that I have the same patient that he showed up in one hospital and he also showed up in the other hospital. When I merge the data, I want to make sure that these two records that refer to the same patient are merged together because they're talking about the same patient. Or if you are starting your career in computer science or science, you go to Google Scholar, you look at your papers. So I can have two papers of mine that appear in Google Scholar in two different places. And I would like to do deduplication, say those two entries refer to the same paper. So this is a very important task in databases. When you have a big database, you want to detect when you have records that refer to the same point and merge them together. This is called deduplication. Now in deduplication, what is important is that I will not merge far points. I don't want it will be really shameful if the hospital has a record of a kid, which is a boy of age 9, and a woman who is 70 years old, and the deduplication algorithm will tell you, oh, it's the same patient. So when you do deduplication, what you want to emphasize is never merge far points. Here is another task that will have a different requirement. So if, say, I want to cluster people to predict a viral spread, say of COVID or of a rumor. Now, if I want to predict in which groups will the virus reach, now what I want to emphasize is that if two people are close to each other, it's likely that the virus or the rumor will jump from one to another. So if I want to do clustering for predicting viral spread, or for example, if I want to do clustering of trees in forests to protect against fires. So I want to emphasize that if I have two trees which are close to each other and one of them catches fire, it's likely that the other one will catch fire. So if I want to do cluster for predicting viral spread or fires or whatever, I want to emphasize that close points will always be in the same cluster. So it's a different task and it wants to emphasize a different aspect of clustering. Or let me give you yet another example. Say I want to cluster neighborhoods for school districts. I am the municipality and I want to say all of the kids that live here go to this school, all of the kids that live there go to that school. I need to cluster the neighborhoods. Now I have to also worry about balancing the size of the clusters. I don't want to have one school with 10,000 kids and the neighboring school has only 10 kids in it. So if I do clustering for distributing school districts, I need to introduce yet another consideration, balancing. So what I'm trying to say is it's not only that the algorithms, each of them prioritize a different requirement, but it's also the reality, your task. You have to be aware of what requirements are relevant to your task. So the bottom line, we really need more awareness of which clustering algorithm you use. So you can ask yourself, how is it being done in practice? And this is a talk that when I give it to an audience of people who are already working, then I ask them, what clustering do you use? And in practice, I ask people, how do you really use the clustering how do you pick your clustering that you use? I mean, 2 weeks ago, I was in a conference in Bordeaux about applying machine learning to health science. And there was a doctor talking about, it turns out that in France, 1% of the population, it's amazing, had surgery in order to lose weight. And there are different surgeries to lose weight, and they want to cluster the patients to predict the results of the surgery, of which surgery will work best for them. So I was asking this doctor, they are using clustering. I was asking, what clustering method do you use? And he say, K-means. And I asked him, why? He said, oh, but that's the only one I know of. So in practice, these are very smart people. This is done by the most ad hoc manner. Doctors, physicists, astronomers, everybody, even computer scientists, will ask them, why do you choose the pathway? So the answer that you get is, it's easy to use. I don't need to tune any parameters. That's why I choose this clustering. And this is like saying, you know, oh, it's freely downloaded software. So why do I use this clustering because I could download the software freely. Oh, I mean, and these are very smart scientists. And the clustering, as we see, makes a lot of difference. Or they give me answers like, it worked for my friend, so I know it's a good clustering method. But maybe your friend had a different problem. I mean, I had two parents my two parents were old and they passed away, but 10 years ago, my father had a cold, his flu, and I come to visit them, and he is kind of obsessively drinking Coca-Cola. And I asked them, why Coca-Cola if you have a flu? So, oh, your mother, she was sick a few weeks ago, and she was she was advised to drink Coca-Cola. It turns out that what she has is a stomach virus, and they believe that Coca-Cola helps you stop diarrhea. But if it will help her for the stomach virus, you think it will help him, although he has a different disease. And that's the way scientists talk about how did they pick the clustering algorithm. Or they pick an algorithm because it runs fast. So if I keep going in this, very common, you see, my algorithm performs all others. And this is the same as saying, this medication is the best medication, regardless of what your sickness is. It's exactly the same statement. And this statement, I mean, there can be no universally good algorithm, or the answers that you get, my algorithm is wonderful. This is an algorithm that can be implemented in linear time. It's just that, you walk into a pharmacy and you tell them what you have and say, buy this pill because it's only 99 cents. And this is just as important if you care about your application. Another is that you see a lot in papers, checked against inherent structure in the data. You run your algorithm, you look at inherent structure in the data, does it match? So that's very nice if your data looks like a collection of nice separated clouds flying in the sky. But, what about experimental evidence? I read papers, I review papers for so many conferences, and so often people use clustering and they give experimental evidence. I can assure you that for every 2 reasonable algorithms that you will give me, I can find data on which one of them looks better than the other, and data in which the other looks better than the one. This experimental evidence just showed me, yeah, the clustering works for this particular set, or worked. And it's not just stupid people. This is an article from Science. And these are, I don't know if you can read the yellow thing. This is from a group, a very strong group, Yuri Leskovich in Stanford. And he writes in Science, and he says in the yellow, this framework provides mathematical guarantee of optimality of the obtained clusters. And I read it and I want to blow up. What is optimality of clusters? What does it mean? We just saw that for different purposes, you need different clusterings. And these are best professors in Stanford. So what I'm saying is that there is a lot of ignorance here, even among very smart people, and there is not to be done. And if you remember my talk from yesterday, you can guess what I will tell you next. What was the lesson from yesterday? You need domain-specific knowledge. There is no universal learner. There is no universal solution to clustering. Whenever you have a machine learning problem, you have to take into account domain knowledge. And the question, so turning clustering into a well-defined class, one needs some bias, some way of preferring one solution over another solution. And for that, you need domain knowledge. This is back to the rats and the pigeons. And so now the question is, how do we do it in reality? How should we go about clustering? Because we know that the way things are being done now are not being done well. So I was considering 2 approaches. One approach is kind of axiomatic. you will formulate properties of clusterings that allow translation of prior knowledge into guidance of algorithms. So for example, the properties that I showed you before. You want a clustering. Do you want your clustering to make sure that close points are together? Do you want the clustering to make sure that the cluster sizes are balanced? So I want to have a list of properties that I will be able to introduce them to the domain expert, to the whoever needs the clustering, and they will be such that I can translate them into algorithm advice. That's the axiomatic approach. Another approach that we tried is interactive. You interact with the user and you give them you ask for some advice from the user as you do the clustering. Maybe the user can tell you. So let me elaborate a little bit about each of those two approaches. The axiomatic approach, there is a famous, in the clustering community, a very famous paper by John Kleinberg from NeurIPS, I think 2006. John Kleinberg is a very distinguished professor at Cornell. And he said, okay, here are axioms for clustering. Here are requirements. So the first requirement is scale invariance. What does it mean? That if you take your data and you scale all the distances by the same factor, you just blow it up without changing proportions of the distances, then if you applied your clustering to the small version and now you apply it to the big version, you should get the same clustering. This is a very natural thing, that it doesn't have to be sensitive to scale. Another axiom that he gave is richness, that he said clustering algorithm, one solution is say, always cluster all the data into one group. That will be scale invariant. That will be wonderful. But you want richness, you want that for every partition of the data, there will be distances such that your clustering will pick this partition. That's kind of richness. And his third axiom is consistency. It says, assume that you had distances and you made your clustering. And now assume that the distance changed. But how did it change? That the distance within clusters grew smaller and the distance between clusters grew larger. So now you have new distances, but the new distances kind of conform with your clustering. They shrank inside the cluster and they expanded between clusters. In that case, you want that if you apply your algorithm on the new data, you will get the same result. Makes sense. All of them make sense, right? But that was Kleinberg's nice results. I'll jump to the results. Anyway, any two of them can be easily satisfied, but the big result is that theorem, those three requirements cannot be simultaneously satisfied. Although each of those requirements sounds very intuitive, you cannot have a clustering algorithm that satisfies all three together. So John Kleinberg gave a long proof because he submitted it to NeurIPS, NIPS at the time, and if you submit a paper to a conference, you have no chance of being accepted if your paper is 2-page. So he wrote a complicated proof, but I have a very simple proof that those three requirements cannot be met together. So it was funny because I was at Cornell when John Kleinberg got the result and he gave a lecture and I was sitting in the audience and he started doing his proof and he said, no, here's a simple proof. So he didn't replace his complex proof by the simple one because he wanted to be a serious paper, but he gave me acknowledgement. You can see acknowledgements to me at the end of this paper. Anyway, so here is the simple proof. What is the simple proof? Assume that by richness, assume that I have one configuration of the data on which my algorithm will pick a cluster separately for every point. And I have another configuration of the points in which I will get some clusters, not every point alone. That follows by richness that by moving the points around, I can outcome two different solutions. Now, what will happen is that by scaling up those, I can get to the picture in the bottom. So if I do scale invariant clustering, the picture in the bottom should be clustered like the picture on the right, because it's just scaling the picture on the right. So by scale invariance, this picture should be clustered like the right. But this picture is also taking every cluster here, every 2 points which are in different clusters grew further apart. And we said that if every 2 points in different clusters grew further apart, the clustering should not change. So by consistency, the new set should be clusters every point alone. But by scale invariance, the new cluster should be clustered like 3 clusters. So we got a contradiction. A very simple contradiction to those 3 very intuitive requirements. So that's the inconsistency or impossibility of clustering paper of John Kleinberg. So the popular interpretation of his result is it is impossible to write axiom for clustering. But what really I think about it is that it's not that you cannot formalize what clustering is that those 3 specific axioms do not work. And in fact, John Kleinberg picked them in order to get an inconsistency result. You wanted to, there is an Arrow theorem on the impossibility of fair voting. Have you heard about it? And Arrow was an economist that got Nobel Prize. So John Kleinberg wanted also to get something like that. So he picked axioms that are inconsistent. So what is the ideal theory? So ideal theory, you should have 2 types of things. You should have axioms that are any reasonable clustering method should satisfy those axioms. And of course, the 3 Kleinberg axioms cannot be thought of as axioms because they contradict each other. And you should have a notion of properties. And that will be properties that distinguish one type of clustering from another type of clustering. So what we envision is having something like that. That here on the top, I have a list of axioms and a list of properties. And on the column, I have different clustering algorithms. And for every clustering algorithm, I say, does it satisfy this property or not? So the axioms should be such that every common algorithm satisfies them. But the properties should distinguish between 2 types of algorithms. One algorithm satisfies this property, but not that property. Another algorithm satisfies this one and not this one. And if you will have such a table, then the hope is that the user will come and say, these are the properties that I need. Now I will search through the lines of different clustering algorithms and find, do I have a clustering algorithms that gets positively the requirements that are needed for my application? So that could be kind of, that's what we were trying to get as an ideal theory. We published a few papers in that direction. We gave up on it. And the problem is, I mean, I think it's a very appealing idea, but the problem is that you want to come up with properties that make sense to the customer, that makes sense to the user. And if you go to the user and say, do you need consistency? Do you need scale invariance? Do you need, it's very difficult for them to give you a good answer. And on the other hand, you want that the properties, the language of the properties will bridge between the user and the designer of the algorithm. That the properties will make sense to the designer algorithm. Because if the astronomer comes to you and say, I want the clustering of the galaxies such that similar galaxies are together or whatever, but what does it mean mathematically? So you want some bridging language between the 2 communities, and that we were trying. We published a few papers like this, and I kind of gave up on the hope. I mean, what I achieved with these papers is that they are accepted to conferences. What I didn't achieve is that anybody is using them. So we tried a different approach, and the different approach is interactive. You're trying to interact with the user and get advice. So what kind of advice can you get from the user? The user can tell you these 2 points should be in the same cluster. If you think about deduplication, for example, you can interact with the data curator and he will tell you, oh, these 2 records are really the same patient. Or he can give you some advice in saying, don't link. These 2 could not live in the same cluster. So maybe on parts of some of the pairs of the points, you could get feedback on should they be together or not. Not everything. If the user knew everything, he wouldn't need you as an algorithm, but maybe on some of the points. Another option is merge split. You propose to them a clustering, and then they tell you, oh, this cluster contains things that should be split. Or these 2 clusters are actually the same cluster. So the user gives you merge or split advice. Another approach that we tried is we say, why do you need an algorithm? So if kind of Census Canada has collection of records of people in Canada and they want to do deduplication because maybe it's the same person that when we did the census last time, he lived in Ottawa and now he lives in Quebec, and it looks like a different record, but for the census, I want to merge it together. Why don't they do it on their own? Because there are 50 million such records, nobody can go through them. But what we can do is can say to the user, I will give you a small piece of your data. I will give you just a few hundred people. And you do the clustering of these few hundred people and give it to me. And I, as an algorithm designer, will try to extract from me the information, what are you really looking for, and put it into my algorithm. So these are kind of interactive approaches between the user and the algorithm designer. And we got some results in that respect. We call it semi-supervised active clustering, in which we start clustering, but every now and then we ask the user on 2 points, what do you think of these 2 points? Should they be in the same cluster or not? And we take it into account when we build our algorithm. So we got some results here that kind of point to me to another aspect. And the other aspect is the issue of runtime. You remember that when we talked yesterday about classification prediction, we said there is the information complexity issue, but there's also the computational complexity. And in clustering, many tasks are NP hard. So we could show that with access to a few such queries, K log n, K is the number of clusters, n in the number of data points. With access to few such queries, we can turn a problem which is initially NP hard into a problem that can be solved very fast in linear time. So this interaction with the user not only helps you understand what the user is after, but it also can help you speed up the clustering algorithm. So that's another aspect of the computational complexity of clustering algorithms, which I will not get into, but that was part of the results that we got here. And it also touches on a different aspect, and this is the notion of clusterability condition. So if you remember yesterday, in answers to questions, I was trying to say that all our theories are worst case, and worst case are not realistic. So the question is, what are realistic assumptions? Maybe under realistic assumptions, things are not as hard. So here in clustering, we assume we want to have a notion of the data is clusterable. Maybe if the data is clusterable, it will be easier to cluster it. And we have a notion of clusterings. So we say that a data is clusterable if there is some factor that distance between points in the same cluster are smaller by this factor than the distances between points in different clusters. So if this notion of clustering makes the clustering easier, and we could get a notion of niceness of data and show that this niceness of data gives you a very strong computation complexity difference. So without getting into the details, what we get here is that we have this parameter gamma that tells you how clusterable is the data. If the clusterability measure of the data is too small, the task is NP hard. If the clusterability measure is greater than 2, then suddenly the clustering task becomes very easy. So there's a sharp, we call it phase transition. You have a notion of niceness of the data. Is the data is not so nice, it's NP hard. The minute the data becomes beyond the threshold nicer, boom, it becomes computably in fast time. But that's so I touched quickly on 2 other aspects. One of them is the runtime of clustering, and the other one is notions of niceness of data. In what sense is data different and worst case? But those are different topics that I will not get on today. So, right. So the conclusion is that we have this, we can cluster with this same cluster, different cluster queries to the user, and according to this parameter of clusterability, we can get fast results. So that's the end of my clustering talk, and I can take questions, and then there are 2 more talks that I wanted to share with you. So yeah, so let me just take questions, and then I will go to other topics. Okay, so both of them are about similar in the sense that it's unsupervised learning as opposed to the supervised learning that I talked about yesterday. And what I want to talk now is about learning probability distributions. So what does it mean to learn a probability distribution? That's a very basic task. So what we want is to learn probability distributions. And what do I mean by learning a probability distribution? So you have an unknown probability distribution that generates data. And you see that's the environment. And you see only a sample of this data, and you want to know that you have the empirical data, and given the sample drawn from this unknown probability distribution, you want to learn as much as possible about the distribution that generates the data. That's a very, very basic, it appears all the way. I mean, we see a sample, we want to know what was the process that generated this sample. And there are 2 types of questions that I can ask. One of them is, of course, what prior knowledge do I have about how the data was generated? What is generated by some kind of, mixture of probability distributions which are unimodal, or was it generated by some hidden Markov process or whatever? And the other question is, what do I want to learn about the distribution? What do I want to learn about the distribution in the reality? So these are 2 different questions. What can I assume about the reality, and what do I want to conclude? Now, the most ambitious task will be do everything. Assume that you have no prior knowledge and try to learn what the distribution is. So you just get a sample, and that many people kind of try to do this thing. You get a sample, tell me what is the distribution that generated this sample. Is it a Gaussian? Is it a mixture of 5 Gaussians? Is it something completely different? Is it a uniform distribution just from the sample? So here is a kind of a diagram. There is unknown distribution D. From this unknown distribution, you get a sample, and you want to crank your algorithm and get some description of the distribution that generated your data. So what I'm saying is that in this general general task is it's very difficult. So here, let me give you an example to explain why it is so difficult to answer it. So consider a lottery. So every week I throw 6 dice and I get 6 numbers, and the ballot that predicted those 6 numbers get, boom, $10 million. That's the lottery, it goes on every week. Now assume that I'm the lottery manager and I wish to cheat. I want to make more money than my salary. So here is a trick that I can use. What I can do and I can toss the dice 1,000 times. 1,000 times, I'll take 10 dice, throw them, and record the data. And I have records of those 1,000 times. Now, in every coming week, instead of tossing fresh dice, I will just give you random answer from my records, from the 10,000 that I collected. You can easily see that now I have a big advantage, because now I can buy 1,000 tickets, and it costs me, I don't know what, 1,000 tickets cost me $2,000, and I write in them all the 1,000 results that I know I'm just picking from those, and I will be the winner, for sure. Now, the question is, if you are an observer and you just see the results of the lottery, how long will it take you to detect that I'm cheating? You see, you are just watching the lottery results every week. The first week it was 2, 3, 4, 6, 6. The second week it was 2, 2, 3, 4, 5. I don't know. How long will it take you to realize that I'm not really throwing fresh dice every time? Because my trick was very nice. I did collect random choices, and now I'm randomly picking from these just 1,000 results rather than some billions of results that are possible. What do you think? When will I be caught? I think that I will nobody will be able to catch that there is a cheating here before the same outcome of the dice appears twice. If you see the same outcome twice, then something is suspicious here, it's not likely to happen. But it will take many, many weeks. By that time, I will be very, very rich before you realize. But you see, this is the problem of you see a sample, you're trying to detect whether the distribution was random throwing dice or the distribution was some picking from 1,000 results, and you cannot do it. So I can phrase it formally, and there is a theorem here, provable impossibility. It is unconstrained density estimation is impossible. And if I want to give you a proof, is basically, consider a domain set of size, finite size n, and look at a uniform distribution. If I uniformly pick from a set of size n, as long as the number of samples that I have is less than square root of n, then I'm not likely to see the same point twice. The birthday paradox tells you that if you randomly pick between n numbers, when you reach square root of n, it begins to be likely that you will see the same birthday twice. But before square root of n, you don't see any number twice. But as long as you don't see a number twice, you cannot tell whether it was the uniform distribution over the whole set, or it was just a uniform distribution over a subset, a small subset, like the 1,000 dice that I collected. Because they all look the same, as long as there are no repetitions. So the conclusion of this theorem, and that's basically the proof, is that if you have some domain of results, as long as you don't see at least square root of the size of the domain, which is unrealistic. I mean, if I try to learn a distribution over real numbers, I want to get square root of infinity. But even if I disk every realistic situation, you never have enough data as square root of the domain size. And as long as you don't see square root of domain size, you cannot tell the difference between those very, very different distributions, the cheating distribution and the real uniform over everything. So the conclusion is, I told you there are two tasks. If you wanted a sample guarantee that limits the sample size, you cannot solve both of them together. You cannot find what the distribution is without making assumptions about what could have been the distribution. So one solution, one kind of direction of research is say, let us assume that the distribution came from a restricted family of distributions. Say, we assume that the distribution is a mixture of Gaussians, and now under this assumption, tell me what is the mixture of Gaussians. And that's the problem that we solved in NIPS 2018. that how many samples you need under the assumption that your data came from a mixture of Gaussians. So that's one direction, make assumption about how the data is generated. There is also a different direction, and the different direction is say, I don't require to know what the distribution is. All I want to do is to answer some limited information about the data. Say, I want to be able to cluster the data. I want to be able to predict labels based on this data. I want to know what is the mean of this data. I want to know what is the covariant matrix of the data. So here I'm saying, instead of assuming that the distribution is coming from a restricted class, I say, oh, I don't assume anything, but I'm trying to learn less. I don't ask you what the distribution is. I just have a collection of questions about the distribution that I want to be able to answer reliably. So these are two separate directions of research. And we have results in both directions. The learning of mixture of Gaussians is one direction, and I will not talk about it in this talk. And I want to talk about this other direction of extracting some answers about the distribution. So this is the focus of this talk. We want to characterize what sets of questions you can answer reliably. We know already that if your question is what is the distribution, you cannot answer it reliably from a finite data. So remember, for binary classification task, if I want to know what's doable and what's not doable, I had the visit dimension. So can we get a similar characterization for the set of questions about a distribution that I will be able to answer? It's a very natural question, because we have this beautiful result in binary classification. Can we replicate it when we learn about distributions? Okay, so let me skip the outline of the talk, but it's mainly, I will show a result with Pavel Rubes and Shai Moran and Amir Spiegel and Amir Yehudayev. And we will show that the answer to this question is independent of set theory. So now I'm hitting you with something which is completely theoretical. You know, there is the famous Gödel undecidability result that tells you that there are always questions in mathematics that you will not be able to prove that the answer is yes, and you will not be able to prove that the answer is no. That's in set theory, abstract set theory, and we show that this is the situation for the question of what can you answer about the distribution. You will never be able to know the answer. You will never be able to prove an answer. That's a very abstract set theory, but it's an application. It turns out to be the case here. But I will try to explain in more accessible terms what we will show here. So I will look at this question of, that's the next talk. Okay, so the general learning approach is, so you have a collection, H is a collection of real valued functions, of queries or random variables. So you can think of X as H as asking, what is the mean of the distribution? It's a number, but this number depends on the data. Or what is the range of the distribution, or of 90% of the distribution? And the answer will depend on the data. So those are called random variables. And I have a collection of random variables, a collection of questions that I want to answer based on seeing a sample of the data. So the input is a sample of the data, and the output should be estimate an answer to every question in my class H. So one solution is what we call uniform convergence. Uniform convergence means that if you see enough data, you will be able to answer all of those questions reliably. And for uniform convergence, that's one tool. One tool is answer all of them together. That's uniform convergence. And it turns out that we know how to do this task, that the visit dimension solves it. But there is an easier learning problem. And in many cases, that's the learning problem we care about. I don't want answers to all of my questions. but I want to find the best model. So you have H is a collection of random variables, and you have a sample as before, but rather than estimating answer to every H in H, what I'm saying is find me an H that has the largest value. So maybe to make it more concrete, say you have a collection of, what shall I tell you? I mean, I have students that are applying to school, and I don't want to find out the distribution of the students, but I want to say which country are most of my students coming from. So every country is a random variable. What percentage of my students are coming from this country? And I'm not trying to estimate the percentages of all the countries. I'm just trying to find which country has the largest application percentage in my pool. You see? So I'm not asking to find the proportions of every country. I'm just asking which is the heaviest. And we call it Emax, expectation maximization. Find me the variable that gives me the largest answer. And of course, it depends on my random sample. In one random sample, I can think that most of my applicants are from Iran. In another random sample, I can think, oh, it looks like most of our applicants are from China. Okay, so this is the problem that we want to learn, and it turns out that this is a very practical problem. So for example, in binary classification, I can consider my sets as the set of all pairs, X and 1, the set of all positively labeled points. And I can say, I want to find the set of positively labeled points which is most likely to occur. So I can model binary classification in this sense, or multi-class prediction. I want to find what function gives you the best results, or case-center clustering. Many problems for case-center clustering, I talked about it yesterday, right? You want to find the best case centers. So for every case centers, you have a value. How good would it be to put my pizza stores in those places? So I don't want to answer all of the possible locations of pizza stores. I just want to find the location which is the best. That's Emax. Rather than answering all the questions, I want to have the answer that gives me the highest value. What's the location that gives me the best profit for my problem? So this Emax is a very practical problem. Many problems can be cast as Emax. And how are we going to solve it? So if we look at here is kind of maybe a summary of more than what I did yesterday, but a summary of basic machine learning. We have a collection of tools in our disposal. So one of them is spark learnability, another one is empirical risk minimization. You remember yesterday we talked about learning with empirical risk minimization, learning with an algorithm that finds the best behavior on the sample. Or another one is weak learning. I think I mentioned it yesterday. Weak learning means that instead of finding the best answer, you want to find an answer which is roughly close to the best, in a very notion of rough. This is weak learning. Another is uniform convergence, I just mentioned it. Another one is an existence of sample compression schemes. Can you compress your data? You get a big collection of points, of training points. Can you compress it to just a few points that will tell you all the story? And another one is the combinatorial dimension, like the VC dimension. And it turns out that in binary classification, all of those are equivalent. If I give you a class and ask you, is it learnable? It is learnable if and only if. It is spark learnable if and only if. It is weakly learnable if and only if. It has compression if and only if it has finite VC dimension. All of those tools give me the same answer when I talk about binary prediction. So binary prediction is the clean case. The fundamental theorem tells you that a class is learnable if and only if all of those above, they're all equivalent. If one of them holds, all of them hold. Now, the problem breaks down once we go out of binary classification. So in 2010, we already showed that instead of binary classification, assume that you want to do multi-class. What is multi-class? You have documents and you want to classify, is this document about movies? Is this document about sports? Is this document a legal document? Is it a medical document? So you want to do classification into many groups. Once you want to do classification into many groups, it turns out that not all ERM algorithms are the same. You can have two algorithms that behave similarly nicely on the training data, but on the real distribution, one of them will be good and one will be very bad. So this equivalence that is so nice, the fundamental theorem of machine learning, was binary prediction breaks down once we go to more interesting, to more complex prediction tasks. Definitely when you go to structure prediction or to graph prediction, or I don't know what any of you is working on. So we don't have this clean, it came as a surprise, but going from two-class problems to multi-class breaks down this equivalence. Now, what about this probability maximization? So here is a very simple task. I give you a collection of subsets of the data, say the origin of my students, those that came from Iran, those that came from China, those that came from India, a collection of a partition of my data, and I ask you, find the class from which I have the highest percentage of applicants. This is a typical example of my Emacs problem. And here, we already see that the equivalence breaks down. And if my collection of classes contains all the possible subsets of the data, then you can always tell me which subset of the data is the highest likely. If you have all subsets of the data, which subset is the highest likely? The whole data set. The whole data set, I will get it from there with probability 1. You see, it's not just a partition. I can ask you, one set will be from Southeast Asia. One set will be from, I don't know what, the Southern Hemisphere. One set will be, so if in my collection of the sets, I have the collection, one set that says everybody, oh, that will always be the most likely to happen. So I can answer this even when uniform convergence fails. But so what I'm saying is that the Emacs is an easier problem. Sometimes we can answer it very easily when other more complicated questions are difficult to answer. Okay, so we wanted to characterize which classes of random variables are learnable in the sense of finding the maximum likelihood one, and can we give a combinatorial characterization? And I see that I'm really running out of time, so let me just mention one tool here that is useful, and that's the sample compression. Sample compression is based on this basic Occam principle. I'm sure that many of you heard about the Occam principle, that the best representation, the shorter the representation of the data, the more reliable it is. That's a very basic principle in science. So what is sample compression? So sample compression is, we have this kind of a game between Bob and Alice. So we have a collection of models F, and Alice knows everything. She knows F, and she knows the distribution that generates the data. And Bob only knows the collection of possible sets. So Alice knows the collection of countries from which I want to estimate which one is more likely. Bob knows it too, but Alice also have full access to the distribution. And now she gets random samples from D, and she wants to get information to Bob, and she is only allowed to pass to Bob few points from the sample that she drew. And the question is, can they agree on a way in which by just passing few samples, Bob will be able to detect every information that Alice had? It sounds very strange at the beginning, but think, for example, that there is a rectangle, that everything inside is red and everything outside is blue. And now Alice knows the rectangle, and she gets a collection of points. She wants to pass a few to Bob. So she can just give him the top and the bottom and the rightmost and the leftmost points. And if Bob knows that all those are red, he knows that everything in between will be red, and he knows that these were the extreme points. We agreed on it in advance. Everything outside will be blue. So Alice can compress all the data in a sample to just 4 points. That's called the compression scheme. And it turns out that a task is learnable if and only if it has a compression scheme. So this notion of compression scheme was introduced by Littleton and Warmuth in 1986. And 30 years later, Moran and Yehudayev, which are both co-authors with me on this paper, they showed the reverse implication, that whenever data is learnable, you have such a compression scheme. That's the notion of compression scheme. That's for binary classification. I will stop following the slides now because we are short in time. I'll just tell you what the basic line is. So we came up with the compression scheme for this Emacs problem. And we showed that this compression scheme, that you are learnable if and if you have a compression scheme. But then we showed that the existence of a compression scheme for a certain problem is independent of set theory. You cannot prove that it exists. You cannot prove it does not exist. And therefore, this task of what types of questions are answered or not in this Emacs model cannot be answered mathematically. So I will stop here. I still have a third talk that I didn't give you, but we'll look for another opportunity. Thank you.